Hey everybody, it's Ripley back again. Oh boy, we're going to open up a whole can of calculus right now. We're going to talk about the fundamental theorem of calculus. All right, now I'm going to dive right into it, but I'm going to dive into it in sort of a crazy way. I'm going to define a new function. I'm going to define a function as the integral from 1 to x of f of t dt. Now, this is going to be my function. This guy right here is f of t. And you may be saying, wait a second, Ripley, what's going on here? I've never seen a function like this. Well, so what? Who cares? Remember, g of x, the independent variable is x. So wherever I see an x, if I'm trying to solve for, you know what, I lied. I don't want to go from 1 to x. I want to go from 2 to x. All right, let's go from 2 to x. It'll be more fun, be more interesting. So if I want to say, for example, I want to figure out what g of 2 is. Let's start with the easiest one. Well, wherever I see an x in g, stick a 2. So this is the integral from 2 to 2 of f of t dt. What do we know? It doesn't matter what f of t is, right? It doesn't matter what it looks like. The integral from 2 to 2 of any function is always 0. That's easy. How about g of 1? What would g of 1 be? Well, g of 1 would be the integral from 2 to 1 of f of t dt. And if we look at this guy, let's take a close look. Well, I'm going from right to left and the function is positive, which means that the integral itself, while the area is going to be 1 wide by 2 high, right? This triangle that has a base of 1 and a height of 2, the area is going to be positive, but the integral itself is going to be negative. So it's going to be negative 1/2 times 1 times 2, which is negative 1. How about g of 0? Well, this is the integral from 2 to 0. And let's see how that one plays out, because that's going to be a little bit crazy. I go from 2 to 0 of f of t dt. And what happens there? Well, I know that the integral from 2 to 0 is the integral from 2 to 1, which we just showed as negative 1, plus the integral from 1 to negative 1. Now, I'm still going from right to left, but the function is below the x-axis, which means I have a negative doubled with a negative. So that's going to make a positive. So that's going to be plus 1/2 times 1 times 1, right? Which is just a half. Negative 1 plus a half is negative 1/2. Let's have a little more fun. What is g of, let's go, what do we want to do here? Let's go g of 3. Well, g of 3 is just equal to the integral from 2 to 3 of f of t dt, which is the area of this rectangle, which is 1 wide by 2 high. This is just 1 times 2, which is 2. How about g of 4? Now we've got from 2 to 4 f of t dt, and this guy's just 2 wide, 2 high, and guess what? I got 2 times 2, which is 4. Last but not least, g of 5 is equal to the integral from 2 to 4 of f of t dt, which is now I've got this rectangle, which we just figured out was 4, plus the integral from 4 to 5, which we know this is a triangle of base 1 and height 2, which is going to be, so plus 1/2 times 1 times 2, which is 4 plus 1, which is 5. Now we can actually graph this curve if we wanted to. Watch. I know that, let's see, what did we say? G of 2 is 0. I know that g of 1 is negative 1. I know that g of 0 is negative 1/2, right? All I'm doing is plugging points. I know that g of 3 is 2. G of 4 is 4. I got to go up here a little farther. G of 5 is, whoa, that should be a 4, right? I put it up at 3. So 2, I'm going to get up into my business on this one. 3, 4, and then g of 5 lives up here, right? So what I have is I've got a curve that goes like this and then comes down. Whoa, that's terribly drawn. And does that. Something like that. Which is crazy, right? We've never defined a function in this way. However, we just did it. So now you've seen it. You don't have to panic. This type of exercise loves to show up on AP exams. In fact, you're pretty much guaranteed to see it a couple times if you're taking an AP exam. Okay, once we have defined that curve, what I want to do is I want to actually talk about the fundamental theorem of calculus part 1 and define what it does. The fundamental theorem of calculus part 1 says this. It says, suppose that f, whoops, ouch, let's go, sorry, I just hurt my knuckle, that, excuse me, g of x is equal to the integral from a meaning it can be anything, from a to x. In this case, I just let a be 2. But the cool thing about the fundamental theorem of calculus is you've got this nice little general form. So the integral from a to x of f of t dt, all right, let's say that that's true. Then this implies that g prime of x is equal to f of x. Now, let me take a minute and sort of describe what this is really saying. Let me get this out of here. What it says is that the derivative of an integral is the integrand. However, we had to do a little mathematical two-step to say, okay, we can't have the integral from a to b because then if I take the derivative of that, we know the integral from a to b is just going to be a constant and the derivative would end up being 0. So what we do is we just generalize. We say, okay, the integral from a to any value, not just b, if I take that thing's derivative, then guess what I get? I get the integrand, which says that the value of the integral is the antiderivative. Notice, if g prime of x equals f, doesn't this imply that g of x, excuse me, that g of x, yes, sorry, is equal to the antiderivative of f? That's really what we're saying. This is true if and only if. This is a definition. Okay, but this is what this guy right here up to this point is what the fundamental theorem of calculus proves. So I'm going to prove that for you guys right now. We're going to go through that this very second. Okay, it doesn't take that long and the ramifications are huge, but I want you to see the robust proof of it. All right, what we're going to do is remember how this is an if-then statement. All right, so we know we get this for nothing. I know that g of x is equal to this guy. I know that I'm going to have to prove that g prime of x is equal to this. So I have this for nothing, and now I'm going to have to work on this. So let's start with g prime of x. What is g prime of x? Well, g prime of x is the limit as h goes to 0. I'm going back. Remember, every time we came up with a new function where we couldn't use a fun little rule to figure out what its derivative was, we always went back to the limit definition of the derivative. So that's exactly what I'm going to do. This is going to be the integral from a to x plus h of f of t dt minus the integral from a to x. This is just f of x plus h, well, g of x plus h, minus g of x. So we're going to have f of t dt all over h. That's all it is. Now, let's think about what happens here. Because we have, remember our addition, if I have the integral from a to x plus h minus the integral from a to x, then think about what's happening there. If on the real number line, here's x, here's x, here's x plus h, and then here's a. If I do the integral from a to x plus h, and I have the integral from a to x, right, of some function, I'm going to have a to x plus h catches all that. I subtract a to x, so all this goes away, and I'm left with the integral from x to x plus h. So I can rewrite this entire thing right here as, this is my side work, sorry, it's in the way. So we can rewrite this as the limit as h goes to 0 of the integral from x to x plus h of f of t dt, and then I'm going to pull out my 1 over h. I'll put it over here, 1 over h, so I don't have to keep writing that big old nasty awful thing. Okay? All right. Good gracious. Now we're going to use an old rule. It's not that old of a rule. It's a relatively brand new rule. We're going to say this. Okay? I'm going to use this rule here. I know that if I think about this, I know that the distance between here and here is h, right? The distance from x to x plus h is h. That's how it's defined. Okay? So if I think about that in those terms, then using this rule, remember, let's go back to this for a sec. Remember, I had a maximum value m, or excuse me, a minimum value m, and a maximum value capital M. And what did that do to me? Well, I'm going to need a little graph here. Here's what we got here. I'm going to pick some weird function. Let's do something like this with it. okay? And I'm going to pick x to be here. Let's pick, I'm going to move x over just a little bit. I'm going to let x be here. And then I'm going to let x plus h, let's let over here be x plus h. Now, according to this rule, with my little m and my big M and then this guy right here, according to this rule, hopefully we see a couple things. The first thing is that from x to x plus h, this appears to be my little m. Let's use some different colors here so we can see what's going on. This appears to be my little m. And then this guy up here, I need to extend that a little bit. This guy appears to be my big M. However, that's not as important as to realize that we're going to let that correspond to some u down here, and then this is going to be some v down here as well. So in other words, I've got an x value somewhere between x and x plus h, such that I will always have a minimum value somewhere on the closed interval from x to x plus h, and we're going to call the x coordinate of that u, and then we're always going to have a maximum value on the closed interval from x to x plus h, and we're always going to call the max value of that capital M, but we get that at v. Now, if that's true, then this little m is going to be f of u, and this big M is going to be f of v. Okay, that's easy enough. Now, if you recall, let me back up just a titch. Look at this. Remember this guy right here? We had all our little rectangles and we said that the integral was wedged between. So I'm going to write one more little piece of information on this page and then I'll skip over the other so we have a little more room. I'll be flippy-flopping back though. According to that rule, I know that this rectangle, let's do this little rectangle right here is h wide and f of u tall. Right? And I know that that is always going to be less than or equal to the integral from x to x plus h of f of t dt. And I know that that is always going to be less than or equal to the rectangle that is m tall, or f of v, and h wide. So this is going to be h times f of v. Now, all I did to write this statement right here was use this rule. We're wedging it between the small rectangle and the big rectangle, right? And that seems like the most intuitive thing ever. So remember, I'm gonna come back just a sec. Our original, I know that G, let's be a little more official with this one. We'll go back to black. All right, I know that G primed of x is equal to the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. And what we're trying to show is that this is equal to f of x. That's what we're trying to do. All right, now we just wrote that h times f of u is less than or equal to the integral from x to x plus h of f of t dt, which is less than or equal to h times f of v. Now you're probably seeing something here. What do we got here? I've got an h here and I've got an h here, and I want an h here to be able to prove my fundamental theorem of calculus. So remember, inequalities, h is positive, so if I divide through by h, I haven't changed the inequality at all. So I can rewrite this as f of u is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to f of v. Now, what's the only thing that I have to do? I got to take the limit as h goes to 0. So if I take the limit as h goes to 0 of this whole thing, you know what, I'm going to save some time. As h goes to 0 of this whole thing, let's just dial it back. The first thing that happens is we know for sure by definition that this is going to be g primed of x, right? Now let's look at what happens to f of u and f of v. I'm going to dial it back here. The limit as h goes to 0 of f of u and f of v, what's going to happen? Well, as h goes to 0, x plus h slides back towards x, doesn't it? So it's like think of these as beads on a wire. As h goes to 0, u and v get crammed closer and closer and closer and closer together, right? And they both head for x. which implies if u and v head for x, if their limit is x, then the value on the function that we head for is f of x, both of them, right? Because u and v are always between, they were defined as being values between x and x plus h, which means g prime of x is wedged on the left by f of x and wedged on the right by f of x, which by the sandwich theorem or the squeeze theorem implies g prime of x is equal to f of x. And guess what? We just proved the fundamental theorem of calculus part 2. Now, all right, that's the proof. Now let's not get crazy because we got to be able to use this thing. The first thing that I want you to realize is if we have a simple function, if I have h of x is the integral from 17 to x of sine of t squared dt, then what is h prime of x? Well, it's going to be what? According to the fundamental theorem of calculus, I know that if g of x equals the integral from a to x of f of t dt, then this implies that g prime of x is equal to f of x, right? So in other words, just stuff the x wherever you see the t. So h prime of x is equal to the sine of x squared. All right, that's one thing. Now what about if h of x equals the integral from x to 17 of sine of t squared dt? Well, we got ourselves a little trouble. And here's the problem. Fundamental theorem, this is FTC, fundamental theorem of calculus only works one way. It's got to be from a to x. But good golly gracious, thank God we have that rule about integrals where I can flip the limits on the integral, right? So I can rewrite this as negative the integral from 17 to x of sine of t squared dt, which implies h prime of x is equal to negative sine of x squared. Now you may be going, wait a second, really? How can the derivative of this thing be this function? Well, the derivatives of all functions of x are still functions. It's just a crazy looking function, right? Does that make sense? Okay, now, this is where it gets a little beefy. What if h of x is equal to the integral from 17 to x cubed sine of t squared dt? Okay, this implies that h prime of x is equal to what? Now, this is where it can get really confusing, but if you keep your eye on the prize, you're going to be golden. Remember, in this case, I am composing an x cubed into the original h of x. Hey, wait a sec. Whenever I compose a function into another function and then I take its derivative, what rule do I use? I use chain rule, right? So how is chain rule going to work? Well, we're just going to follow the end of our noses. The first thing that we're going to do is we're going to stuff the x cubed wherever I see a t. So this becomes sine of x cubed. However, careful, it's t squared, so this is going to be squared. And then I have to multiply by the derivative of the thing that went in. Now you may be going, wait a second, Ripley, what is going on? Well, like y equals, if I want to take the square root, the derivative of the square root of 1 plus x cubed, right? Well, I know y primed is the derivative of the square root, which is 1 over 2 root 1 plus x cubed, and then the derivative of the thing that I composed in there. So that would be times 3x squared. Sorry that I did that at a diagonal. I wanted to conserve a little bit of space. So the x cubed, in this case, not a 1 plus x cubed, but the x cubed is being stuffed in where the x used to be. So I'm going to have times 3x squared. In a puff of algebra, I would rewrite this because I like this 3x squared as a coefficient better. Then I'm not confusing it with an angle. So this just becomes 3x squared sine of x to the 6th. I'm done. Let's do one more of those. How about h of x is equal to the integral from 17 to root x of sine t squared dt? Well, that implies that h prime of x is equal to, well, remember, just going to stuff root x wherever I see a t. So this is going to be sine of root x squared, which is just x, times the derivative of the root x by chain rule. This guy shows up by chain rule. This guy shows up by chain rule. And then we could fix it up algebraically. All right, now I'm going to come over I'm going to do one more rule with you guys, and then I'll give you the fundamental theorem of calculus part 2, which is really the sweet spot, and then we're done, okay? Last but not least, what if I let h of x equal the integral from the square root of x to, what did I say, x cubed of sine of t squared dt? Well, again, fundamental theorem of calculus is a one-trick pony. You have to make it look like that. In other words, I have to go from a constant to a function, but that doesn't work. However, there's this fancy little trick. And that fancy little trick is, if you recall, I can bust up an integral by inserting an arbitrary constant in between the lower and the upper limit. I can take the integral, I can rewrite this integral as the integral from square root of x to a of sine t squared dt plus the integral from a to x cubed of sine of t squared dt. That plus sign looks a little too much like a t. I don't want that to get confusing. Now again, not allowed to have the a on top. So what I do is I'm going to flip it and put a negative out in front, and then I'm going to use the commutative property of addition to send it over to the other side. So this becomes the integral from a to x cubed of sine of t squared dt minus the integral from a to root x of sine of t squared dt. And now I just apply the fundamental theorem of calculus twice and I'm done. Right here, do what we did before. The derivative of this is going to be sine of x to the 6th times 3x squared minus, now I deal with it, that took care of this guy. Now we're going to do this. And this is sine of the square root of x squared, right, which is just x, times 1 over 2 root x. So this turns into 3x squared times sine of x to the 6th minus sine of x over 2 root x. Whew! So the general rule, if you think about this, if h of x is equal, you know what, let's do it differently. This might get a little confusing with the repurposing of h of x, but don't worry about it. If I do the integral, if I let y equal the integral from h of x to g of x of f of t dt, then the derivative of that guy is f of g of x times g primed of x minus f of h of x times h primed of x. And if you're like, huh? Where'd that come from, Ripley? We'll just go back and look at this example. Okay, last but not least, we're going to do the fundamental theorem of calculus part 2, and then we got everything, okay? And I'm actually going to prove an integral that I took earlier, and I'm going to show you how I did it. The fundamental theorem of calculus part 2 really gives us a practical way to use definite integrals. It says that the integral from a to b of f of t, of f of x dx. Now I don't have to do the little presto changeo thing with my variables because this is a definite integral. I'm not going to prove the fundamental theorem of calculus part 2 because you're probably not going to watch it, but I do want you to see it, all right, because you're going to use the heck out of it. All right, here's what happens. The integral from a to b of f of x dx, f of x, let me rewrite this whole thing, this is annoying me, of f of x dx is equal to the antiderivative of f of x evaluated from a to b. Now notice, this is what's important in my class. I want to see the integral sign on the left become a straight line on the right. That tells you that you actually took an antiderivative. As these get more and more complicated, you're going to be doing a lot of algebraic and calculus trickery, and it can get really confusing in terms of whether or not you actually took an antiderivative or not. This is a way to let yourself know. And this is equal to f evaluated at b minus f evaluated at a. So if you recall, a while ago, we took the integral from 1 to 3 of x squared dx. And I can't remember what we got, but I think it was something like 26/3 or something like that, but we're about to figure it out. What I do is I'm going to show you how it's done. Take the antiderivative of x squared, which is x cubed thirds. I'm going to evaluate from 1 to 3. Now this negative right here is going to give you fits if you don't give it the respect it is due. So this turns into 3 cubed thirds minus 1 cubed thirds, which is 27 thirds, which last time I checked is 9, minus 1 third. Well, 27 thirds minus 1 third is 26 thirds, which is the exact same thing that we got before. You're going to use the heck out of this. This notation right here and this use of the said notation right here is never going away as long as you take definite intervals, which is what we're going to do for the rest of class. Okay. Oh, rest of literally the course, not just class. All right. Thanks for listening to me, you guys. Hope you have a great day, and I'll see you in the next lesson.